Mm. Okay. If I remember, we have done this expression, right? That is resist. We compared the metallic conductor with the electrolytic conductors, correct?
Yes, ma'am.
Okay. And the main idea that we brought out was in the case of metallic conductor, the electrons are the charge carriers, whereas in a electrolytic conductance. Okay, the moment I say electrolytic conductance, don't like go to electrolytic process. Okay, we are trying to pass the current through a solution. Okay, we are trying to pass the current through a solution and checking whether the current does flow through the solution or not. So the current does flow through the solution provided it is having ions. So the charge carriers are the ions. Clear?
Yes, ma'am.
Okay, okay. The other most important aspect is that the resistance was directly proportional to temperature, whereas here the resistance is inversely proportional to temperature. Okay, with these two, we are now stopping our discussion with respect to metallic conductance. And now, whatever discussions we have, that is for an electrolyte or a solution, electrolytic solution. So we will start now. As in the case of metals, the expressions is same. R is equal to rho L upon A. Last class we were writing the units, etc., for all that. If R is represented in ohms, L in centimeters, because I told you the cell which we are going to use for storing the solution and carrying out the experiment is not very large. So we take the dimensions of length in centimeter itself. Okay. And therefore the rho will become ohm centimeter. Ohm centimeter. Rho is defined as that much resistance when L is 1 and A is 1. Are we clear? Rho is the resistivity, which is the resistance offered by a solution when the length of the distance between the two electrode is 1 unit, and the area of cross section of the electrode is also 1 unit square. Any doubt about this?
No, ma'am.
Okay. And also I discussed about something called as 1 by rho is equal to kappa. As rho is resistivity, kappa is supposed to be conductivity. Okay. So the conductivity's units will be exactly inverse of the resistivity's units, which will be ohm inverse, centimeter inverse. Okay. Now, whenever you want to find out the current carrying capacity of a solution is not a rigid substance. Therefore, we would use a cell which is or a container. I told you here the word cell refers to a device which stores the solution. So we take the electrolyte and store it in a container. Okay, I have drawn a disproportionate diagram where the length is 1 unit. Okay, assume that it is 1 meter and the area of cross section is 1 unit square or 1 meter square. If I'm again using a large length, large surface area, but in reality, it is mostly a smaller one. Say, for example, 1 centimeter and 1 centimeter square. Okay, unit length and unit area of cross section. Any problem with that?
No,
Any
ma'am.
problem? Okay. Now, the electrodes are attached on the ends of these cells, and the electrodes are at 1 unit length, and the area of cross section of the electrode is 1 unit square. So I'm just going to remove the centimeter. Last time also I did this, I remember. Just for the revision sake, I'm doing 1 unit square. Assume, of course, when you have 1 centimeter length and the area of cross section is 1 centimeter square, the volume that you will store will become 1 centimeter cube, correct? Length
Yes,
into
ma'am.
area. Huh. But for simplicity, I'm going to take it as 1 liter. Okay. Just for the sake of simplicity, I'm going to take it as 1 liter. I could have taken it as 1 centimeter cube also, nothing wrong. But the discussions will be similar. They will not be different when the volume is different. Okay. So we were talking about the solution. Supposing I have got 1 mkcl, and if the volume of the solution stored is 1 liter, 1 unit, 1 liter, then the amount of electrolyte is going to be 1 mole. Okay. 1 m refers to 1 mole per liter. If I'm going to take 1 liter of the solution and pour into this container, which is called as electrolytic cell, then that will offer me 1 mole. Any confusion in that?
No, ma'am.
Okay. Supposing I increase the concentration to 2 m, that means it is 2 mole per liter. 1 liter of this is going to offer me 2 moles. Again, we concluded that electrolytes or electrolytic solution, electrolytic conductance is due to the availability of ions. So, when you have more ions, you can expect that the current carrying capacity is increasing. So, this current carrying capacity, the conductivity, becomes directly proportional to concentration. And I gave you exactly the words. With increase in concentration, the number of ions per unit volume increases. And hence, as you have more charge carriers, more current carriers, the current carrying capacity will increase with increase in concentration and will decrease with decrease in concentration. Any doubt about this?
No, ma'am.
Mm. Okay, now coming to something called as molar conductivity. So we have the data with us. Okay, the data about the conductivity and the molar conductivity. Apart from this, of course, there are other electrolytic conductance also depends upon the nature and the structure of the metal. Not all metals are good at conduction. Not all metals are equally conducting, correct? The best conductor is said to be the silver. Okay, and copper. Apart from that, other metals, iron, aluminium, etc., are also good. Apart from that, there are some metals which may offer great resistance also, like tungsten offers great resistance, and because of high resistance only, it is used to make the filaments, correct? It offers high resistance. When there is a high resistance, the electrons struggle. This is about the metallic one. The paragraph is about the metallic one. So assume that tungsten offers a lot of resistance. That means the electrons are traveling from one point to the other and they face a lot of resistance. Overcoming the resistance means a lot of movement, lot of friction. Temperature will soar up. As the temperature soars up, the filament glows. Okay. So some metals have lot of resistance, some metals have got very less resistance. The number of valence electrons per atom. More the number of valence electrons, more the current carrying capacity. Okay, temperature. It decreases with increase in temperature. Coming to the solutions. It depends upon the nature of electrolytes. Some electrolytes are completely dissociated. For example, if you take NaCl, the KCl is better dissociated than NaCl. NaCl is also almost 100% dissociated, but KCl will be better. CH3COOH, it ionizes, but we know that it partially ionizes. Correct, children?
Yes, ma'am.
So it depends upon the nature of the electrolyte. Okay. It also depends upon the size of the ions produced and their solvation. Just give me a minute, children. Yeah. Okay. This thing is very important, though it is not discussed in the textbook, children. There is an trend. The larger cations show greater mobility than smaller cations. Please note the point. Supposing I'm talking about group 1 ions, okay? Then we have got rubidium. The francium is largest, but rubidium cation is next largest. So your lithium, sodium, potassium, rubidium, and cesium. Sorry, cesium is the largest. Cesium. So cesium ion conducts the best. Okay, and the conductivity by the smaller ions keeps decreasing. Isn't it surprising, children? A large cation is doing better conduction than smaller ones.
Yes, ma'am.
Okay, the reason is that a large cation, assume that you have got lithium cation, it's small. Okay, so one positive charge is spread on a smaller surface area. When you go to sodium, one positive charge is spread on larger one. Potassium, one positive charge on a large surface area. And as we move to the last one, the cesium, francium is radioactive, so we don't carry out the talk about that. So cesium is largest. What happens is, as a single positive charge spreads on a large surface area, the charge density decreases. As the charge density decreases, it's free of solvation. What is solvation? Assume that you are traveling from one point to the other. Another instance, you are traveling from one point to the other carrying a big bag. Where are you going to travel faster? In which situation are you going to travel faster?
First situation.
Yeah, where you don't carry any load, correct? The load here, in the case of ions, is the solvation with high positive charge density. Lithium is very small, high positive charge density. It will be attracted to many water molecules. It will be surrounded by many water molecules. H2O, 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 H2O. So the overall baggage becomes large. And with such large size, it is unable to move. With high positive charge density, it gets attracted to many water molecules. Are we clear? Yes?
Okay, ma'am.
Aprameya?
Yes, ma'am.
Okay. With increase in the size, the charge density decreases. When the charge density decreases, it is not that very attracted to the water. So the overall baggage size reduces. It's only the ion, not the water with it has to travel. So it is free of those water molecules. It is not loaded with lot of water molecules. Whereas here, lithium will be loaded up with lot of water molecules. The number of water molecules keep decreasing. By the time I come to cesium, very few water molecules are there. So mobility is affected by the hydrated ion size, not the ionic size. It's depending upon the hydrated ion size. Are we clear?
Yes, ma'am.
Okay. But hydrogen is the best. Is that not a contradiction? It is the
Yes,
smallest.
ma'am.
It is a contradiction. Okay. Why? It is that if it is lithium, it has to carry its baggage. If it is sodium, it has to carry its baggage. But when it comes to hydrogen, it is not that. Hydrogen, the small hydrogen, will be taken up by first atom. That will be thrown to the second. That will be thrown to the third. So it is being passed on. It is not carried. It is being passed on. There is a lot of difference. If I'm asking you to take a load of something, okay, your school bag and travel to 5 kilometers distance. Your bag has to travel, but you are supposed to carry the bag. It becomes very difficult. Your bag is very manageable weight. But if you have to travel 5 kilometers, then the time taken for the bag to reach the end point becomes large because you travel and you become tired, etc., right? But imagine there are 100 students standing in the pathway of 5 kilometers. There are around 1,000 students making up the queue. And the moment first one takes the baggage, it is immediately transferred to the second, immediately transferred to the third. Where does the bag complete its journey faster, in the first or the second situation?
Second.
Second situation. So hydrogen doesn't travel independently. Hydrogen doesn't travel. Lithium has to travel. Hydrogen doesn't travel. The water molecules in the solution take up the hydrogen, immediately pass it on to the next, immediately that goes to the next and keeps on rolling till it reaches to the water molecule which is located very close to the electrode. So ஹைட்ரோஜனுக்கே ஒரு கேரியர் இருக்காங்க. Understood?
Ma'am, so hydrogen binds with water to form hydronium, and then that
Yes,
hydronium
yes.
is.
It's not hydronium which travels. This is first water. This is second water. This is third water. So the H plus goes to the first water, becomes hydronium ion. The hydronium ion passes on its H plus to the next water molecule.
Okay, ma'am.
So for some time it becomes H3O plus. And the very next instance, this becomes H3O plus. This is getting relieved of that. Hydrogen is being passed on. Got it?
Yes, ma'am.
Okay. So again, in accepting for the competitive examinations, nobody is going to ask you this. That's why the term solvation. More the solvation, less the mobility. More the solvation, lesser the mobility. Next, nature of the solvent. In which type of solvent? The solvent sometimes will be, if the solvent is so polar, supposing the solvent is very, very ionic, and it tries to hold back the Na plus. Na plus wants to go to the cathode, but solvent is holding it back. Viscosity, more the viscosity of the solvent, less the ability of the ion to travel. Got it?
But ma'am,
Concentration.
if the solvent is non-ionic, ma'am, if it's non-polar, ma'am, then that is the best, ma'am.
Okay, again, an ion has to be will an ion be available in a non-polar solvent, Ishan?
No, ma'am. No, ma'am. No, ma'am.
No. So there should be polarity, but it should not be too exceedingly high. Understood?
Okay.
There should be polarity, and otherwise ions will not break off. No, NaCl will stay as NaCl. Is NaCl soluble in CS2, which is completely non-polar?
No, ma'am.
No, no polarity. Like dissolves like. Remember solution lesson. So NaCl is ionic. CS2 is completely non-polar, covalent. It won't even dissolve. So you want an polar solvent, but the polarity should not be very, very high. Okay. Otherwise, it will hamper the movement of the ion. The viscosity should not be very, very. Supposing I decrease the temperature of the water. Think about this. What will happen to the viscosity? The water molecules are going to maybe assume that it is going to get frozen. Viscosity will slightly increase. Particles will come together. Again, traveling of the ions become a problem. Then temperature. It increases with the increase in the temperature. So these are the point of differences between metallic and electrolytic or ionic conductance. Okay, we are further moving to this table. Look at this table. There is one term here. We are going to learn up to this now. Look at this. What is happening? The concentration is expressed in moles per liter. Okay, it's 1 mole per liter. What is the conductivity value? It is 0.1113 Siemens per centimeter or ohm inverse per centimeter. What happens when the concentration is decreased? The conductivity value, don't look at this,
Decreases.
decreases. So kappa conductivity is indirectly proportional to concentration. Concentration is high, conductivity is high. Concentration decreases, conductivity decreases. That's what is evident here. It decreases to 0.010, the conductivity also decreases. This is expressing the concentration in mole per meter cube and conductivity in Siemens per meter inverse. Both are going to reflect the same thing. As the concentration decreases, conductivity value decreases. Any problem with this? Any
No,
problem?
ma'am.
Aprameya?
No, ma'am.
Okay. Now the question is, how do you determine the conductivity? How do you determine the conductivity? For which we have a setup which is called as a Wheatstone bridge. Okay, so what is this Wheatstone bridge? Have you come across Wheatstone bridge in your physics?
Yes, ma'am.
What does it do? And
It
what is the
helps to
setup?
find the unknown resistance.
Very good. Unknown resistance. Remember, R is equal to rho L upon A, and rho is nothing but 1 by kappa. Kappa is nothing but 1 by R L upon A. And we are trying to find out kappa, but we cannot find it directly. So what we do, we find it out by using the resistance value. Okay, so what we are going to do, understand the basic setup of a Wheatstone bridge. There are 4 resistors, okay, out of which 3 are known to us and the fourth one is unknown to us. So our task is mainly to find out. Assume that this is R1, this is R2, this is R3, and this is R4. Supposing I know R3, I know R4, I know R2, and I don't know about the R1. Okay, what will I do? I'll take a rheostat and connect here. So when I connect a rheostat, the symbolic representation is something like this. Am I right?
Yes, ma'am. The arrow should
Okay.
point
Yeah.
downward.
Okay. Is there a convention? I don't know. I'm not a physics person. Okay, like this. Right. So we have to strike. Okay, like this. Okay. So this is R3, which can be varied. Fine. Now we are going to complete the circuit in order to pass the current. And what we do is we use an AC current. Why AC current? Very importantly. We'll come to AC current later on. Okay. Now we have the knowledge of R2. R2 is fixed. R4 is also fixed. R1 is fixed but unknown. Others we know. R2, R4 is fixed and known to us. These are known. Okay, what I'll do is I will change the rheostat or the variable resistance, right? Variable resistance value till no current passes through this circuit, this part from the terminal A to terminal B. Is that clear?
Yes, ma'am.
Okay. Now, how do I do that? I use AC current. So I'm going to pass the current through the circuit and wait till no current flows. That means I can attach maybe a galvanometer and check when the reading becomes at what value of R3 will the galvanometer shows marking to 0. Okay. Or there are a number of other devices like we can use a hearing sensor also. We can use a head plug. Okay, a headphone sort of thing. This is a noise detector, let us say. It's a noise detector. So we can use a headphone, and as soon as the current does not flow, the noise gets totally zero. Any problem with these two setups?
No, ma'am.
Okay. So, Ishan, is that okay?
Yes, ma'am.
Okay. So I'm going to check at what R3, at what value of, because R1 is unknown and fixed. R2, R4 are known and fixed. We know R2, R4. But R3 is going to be known to us because it is handling the rheostat, the alternating, the variable resistance. So we'll move the resistance to that value at which there is no current flowing between point A and point B. So now with that, we also know the R3. Okay. Now, when there is no current flowing through this Wheatstone bridge setup, this whole setup is said to be Wheatstone bridge. According to the principles of Wheatstone bridge, R1 by R2 is equal to R3 by R4. Now, we know R2, we know R4, and just now using the variable resistor or the rheostat, we also got the value of R3. What value of R3 will be such that there is no current flowing between point A and B. So we know R3. Using R2, R4 and R3, we can very well find out the unknown and fixed value of R1. Are we clear? That becomes R3 into R2 by R4. Any problem with this? This is the principle of Wheatstone bridge. Okay. This is how we find out the unknown resistance. Unknown resistors value. Fine. Now, how do we use this setup? Instead of using the R1 as unknown, we are going to connect it with the conductivity cell. Remember, we are going to use a conductivity cell. So, our conductivity cell comes into play. And the conductivity cell is going to store the 1m or any other solution for which you want to find out the conductivity value. So I'm going to use the whole conductivity cell here. Now what? Again, we'll repeat the experiment. We'll keep changing the resistance R3 till the current does not flow from point A to point B. Whatever resistance you measure, that is calculated by the principle of Wheatstone bridge. Any doubt about this?
No.
No, ma'am.
Okay. Now we know the R1. Also, since the conductivity cell or the container in which we poured the solution is only what we used, we know it's L, we know it's A. That means from this expression, we know all the three things. We know the distance between the electrode, area of cross section of the electrode, and from the Wheatstone bridge, we also found out the R value. Can we not use these three to find out the kappa value? Is the
Yes, ma'am.
setup clear? Okay, right. Now, the question is, why do we use an oscillator? Oscillator uses AC. Oscillator is to produce AC current. Okay, think of this. I am trying to find out how good KCl is in conducting current. I'm trying to find out the conductivity value. What is conductivity? The conductance of the solution placed between electrodes at 1 unit distance, the area of cross section being 1 unit square. So the conductivity depends upon the ions, correct? And these ions should not get reduced, should not decrease in concentration or increase in concentration. I want the conductivity value of the ions offered by 1 mkcl. Na? So, is it okay if I measure the conductivity for if I'm going to pass DC current? Assume that I'm going to pass DC current. What will happen? The chloride will go and get oxidized, will get converted to chlorine. Okay. And for now, I'm saying potassium also gets reduced. I'm just saying it won't get reduced. We will eventually discover why. So potassium gets reduced. Chloride gets oxidized, potassium. Don't you think the concentration of 1 mkcl will drop to 0.9 or something lower than that?
Yes, ma'am.
If I'm using DC, what do you mean by DC? One
That is
electrode
why.
constantly being negatively charged, the other electrode constantly being positively charged. The negative electrode will promote the reduction, positive electrode will promote the oxidation, and the concentration of the potassium and the chloride ions will drop down. That means you would have found out the conductivity value, but the concentration, but it will be for the concentration which is not 1m, will be less than will be less than 1m. Are you able to understand?
Ma'am, I didn't understand.
See, man. See, okay. See, I'm trying to find out the conductivity of 1 mkcl, Ishan.
Yes, ma'am.
So I have 1 mole of K plus and 1 mole of Cl minus, correct?
Yes, ma'am.
I'm going to pour it into that container and I'm going to attach the electrodes. This is the positive terminal and this is the negative terminal. So I'm going to try to pass current by a direct current. That direct current is what? Where the charges on the terminals do not change. Okay,
Yes,
so
ma'am.
this is positive electrode, that is positive. Well, as you see, K plus ko no agar, nothing will happen to K plus in the presence of water. But still, for this discussion sake, I'm saying that K plus will go and get reduced, and the Cl minus will go to the positive electrode and will get oxidized. So even if the measurements goes for next 5 minutes, if I'm using 5 minutes of constant current supply to the solution, within the 5 minutes, the concentration of 1m drops down to 0.95 m. So you would have
Yes,
measured
ma'am.
the
Yes.
conductivity, but that conductivity is not for 1m, it is for a different concentration. You wanted to find the conductivity of 1m solution, but you are now identifying it for a 0.95 solution. Understood?
Understood, ma'am.
So what we do is we remove this battery and we attach an oscillator. What is an oscillator? It provides an AC current. What will AC current do? For one cycle, this is positive, negative. For the next cycle, this will become negative, this will become positive. The next cycle, this will become positive, this will become negative. So that means ions will keep moving from one electrode to the other, but no net reduction, no net oxidation will happen. But therefore, the concentration will remain 1m. No reduction in potassium, no oxidation of chloride. So potassium ions remain potassiums, chloride ions remain chloride ions. No net reduction, no net oxidation. So the conductivity value that you measure now will be actually for
1M
no
solution.
1m solution. That's why we use. So why DC current should not be used in measuring the conductivity or the resistance through the Wheatstone bridge? Because if you pass the DC current, the concentration of the electrolyte decreases due to reduction and oxidation. An alternating current will keep changing the polarity. It will lead to no net reduction, no net oxidation. Are all the points captured?
Yes, ma'am.
Oh, okay. Now, is it clear, ma? Any problem?
Yes, ma'am.
Okay. Now, coming to one more important concept. What is that? See, now I have, let us say, KCl. Okay. I took 1m solution and measured the conductivity. Fine. When I decrease the concentration, I realize that conductivity increases. When I again further decrease the concentration, I got a higher conductivity. So I know when KCl is going to offer me the best conductance. Okay, as the concentration is reduced, the conductivity value increases. Sorry, decreases. Any problem with this?
No, ma'am.
Okay. But supposing I want to find out how is NaCl as compared to KCl. Okay. I want to compare NaCl and KCl's ability. That means now I have to fix the number of moles. So what I'll do? I'll consider now the solution, the NaCl solution offering 1 mole. So my consideration will be what is the conductivity offered by 1 mole of NaCl as compared to the conductivity offered by 1 mole of KCl. Is it fair to compare KCl with NaCl only if the number of moles of electrolytes are same to one another?
Yes, ma'am.
Okay, very good. So now I go for a new term because I'm interested to compare one electrolyte with the other. When I'm comparing one electrolyte with the other, then I will have to keep the number of moles constant. So let us check as to 1 mole of NaCl is better or 1 mole of CH3COOH is better or 1 mole of the KCl is better. Thus comes the term which is called as molar conductivity. Okay, what is molar conductivity? It is the conductivity offered by V volume of solution. V volume of solution when placed between electrodes. I'm going to show you the book also. Electrodes placed at 1 unit distance and area of cross section A. the moment I use expression V volume and area of cross section A, that means these two are variables. So what is molar conductivity? Crudely, the conductivity offered by 1 mole of 1 mole of electrolyte. But you can't take solid electrolyte and do measurements. It has to be in the form of a solution. So we'll say molar conductivity is the conductivity offered by V volume of solution when placed between electrodes at 1 unit distance having A area of cross section. That means A is bound to change, V is bound to change depending upon the concentration. Now, why is that? Let us see. Supposing I have 1 mkcl. I've got 1 mkcl. I've got 2 mkcl on the other hand. Now tell me, I need 1 mole. And that's when I will call it as a molar conductivity, right? If I
Yes.
measure the conductance offered by 1 mole of KCl, then only I will call it as molar conductivity. Okay. But the concentrations are different. So what will I do? I'll take volume of solution. What volume of solution will offer me 1 mole? Come on. What volume of solution will offer me
1
1 mole?
liter.
1 liter. What volume of solution will offer me 1 mole if the
2
concentration is 2m?
liters.
It's 2m, 2 moles per liter, Ishan. 2 moles per liter. 2 moles. What is the meaning of 2m?
1 by 2,
It's
no?
2 moles. So that means 0.5 liters I'll have to take. Supposing it is 4 mkcl,
0.25.
0.25 liters. Supposing it is 0.1 mkcl, then what will I say? I'm getting 0.1 moles from 1 liter, correct? 0.1 moles from 1 liter. So in order to get 1 mole, what volume should I take? When the concentration is 0.1 mkc, how
Into 10,
much?
ma'am.
Into
10
10,
liters.
10 liters. 10 liters. Fine? Fine? So, I don't want to put the burden on the electrons. So, what will I do? I'll place the electrode at the same distance. Okay, 1 unit. Because the moment you increase the length, what will happen to the resistance, children?
Increases.
Increases. So I don't want to increase the distance traveled by the ions. But what I can give is a large surface area. So I'll keep the distance between the two electrodes same. If I have to pour 1 liter solution, I'll keep the area of cross section like this. But if I want to pour 0.5, what will I do? I'll reduce the area of the metal plates and make our container small to just hold. If this is holding 1 liter, then this is going to hold 0.5 liters. If I want to do the next experiment, what will I do? I'll keep the distance between the two electrodes same. This time, I'm going to use a... So, why am I not increasing the length? The moment length increases, the distance traveled by the ions increases and the resistance will increase. So, this is 0.25 liters. But what if I want to get 1 mole from 0.1? What should be the size of the electrode? Like this, no? Distance is same, but the electrodes will be large, na? Large surface area so that it can accommodate 10 liters volume. Do you get the experiment?
Yes, ma'am.
But each time, whether it is 1 liter or 0.5 liter or 0.25 liter or 10 liter, how many moles of electrolyte goes in? Since it is molar conductivity,
1 mole. 1
it's
molar.
always 1 mole. 1 mole. 1 mole. Not 1 molar. 1 mole. It's always 1 mole. It's always 1 mole. Yes, Ishan?
Why
1
1
mole.
mole?
Because what is molar conductivity? It is the conductivity offered by that volume of solution which offers 1 mole when placed between. Am I not talking about the performance of mole, 1 mole?
Yes, ma'am.
Molar conductivity means what? It is the conductance offered by V volume of solution that offers me 1 mole of electrolyte when placed between electrodes at unit length distance with area of cross section A. I am checking the performance of 1 mole of electrolyte. That is why it is molar conductivity. So, why
Yes,
did we do these volume calculations? What are these volume calculations? Because these volumes will offer me 1 mole.
yes, ma'am.
If you say molar, are you not talking about concentration? Molar. You said 1 molar. Molar means what? Concentration. Na?
Yes,
Concentration
ma'am.
is written here. See, 1 m. How many liters of 1 m solution will offer me 1 mole? 1 liter. How many liters of 2 m solution will offer me 1 mole? So the idea is that I'm asking the performance of 1 mole in different types of solution.
Yes, ma'am.
Okay. Now it's like I'm going to ask you to think this way. Okay. I'm asking, let us say, 100 runners in a small school ground to complete a 100-meter race. 100 runners. Okay. In your school ground from the starting to the finishing line. This is finishing line. Okay. For a change, I'm going to take you to a big stadium. Fine. And I'm going to allow you all to stretch yourself like this. And then I'm asking you to run that 100-meter race. Same 100 people. Will you be more comfortable in running a broader stretch or a narrow stretch?
Broader.
Broader. Ishan, are you able to understand?
Yes, ma'am.
Assume in your school ground, which is a very, very narrow path. In a school ground, I'm asking 100 people to finish this race. This is the starting, this is the finishing point. 100 people will run in this cramped area. Same 100 have to travel the same length, no change in the length. Same distance they have to travel, but each one can spread out from one another. So, where are they going to be better?
Broader.
Obviously, so same thing happens here. 1 mole present in 10 liters. Are we not spacing them out?
Yes, ma'am.
But 1 mole in 1 liter, you're cramping. 1 mole in 0.5 liter, further. 1 mole in 0.25 liters. Do you think where will the same KCl, all the 4 diagrams that I've shown, it's the 1 mole of KCl. Where is it going to perform the best?
10 liters.
Obviously, because what you are trying to do is like if one is running, the others will be there to push him around, correct?
Yes, ma'am.
But in ions, that doesn't happen. When K plus is running, the Cl minus around it will pull it back. The Cl minus is going to pull it back. When the Cl minus wants to travel, the K plus around it will pull it back. So the mobility of the ions will decrease if the concentration is very high. Same 1 mole, very close to one another. Chloride is close to potassium. Chloride will face a drag. The potassiums will drag the chloride back. The potassiums will be dragged by the chloride and they never reach the electrodes. The cation should reach the cathode, anion should reach the anode, which they are unable to complete. Now think about here. The K plus is here. The Cl minus is well spaced out. If the potassium wants to go to the cathode and the chloride wants to go to the anode, the potassium doesn't face a pull from the chloride. Chloride doesn't face a pull from potassium ions. So are
Yes,
they
ma'am.
not becoming free of, are they not able to reduce the inter-ionic attraction?
Yes, ma'am.
The inter-ionic attraction reduces with decrease in the concentration. So where is, so again KCl, I want how the 1 mole is performing. Is it performing best in 0.1 m? Is it performing best in 1 m or 2 m or 3M or 4M, 3M, okay, 4M. Where is it performing the best? Or will it perform the best in 0.01M?
0.01 m.
What volume is going to be considered in this case? What
100
volume will
liters.
100 liters will offer 1 mole. Ions are well spaced out. Potassium is free of chloride. Chloride is free of potassium. No interionic attraction. Potassium is free to go to the cation is free to go to the cathode. Anion is free to go to the anode. So, whereas in 0.1, it is present in 10 liter. Here it is in 1 liter. Here it is in 0.5 liters. If you take 3M, it will be around 0.3. Here it is going to be 0.25 liters. So when 1 mole is present in 0.25 liters, the ions are very close. The interionic attractions are large. Potassium is no longer free to move. Chloride is no longer free to move. Got it?
Yes, ma'am.
Okay. So what do you understand? When is it best performing? When the concentration is low or when the concentration is high?
Concentration is low.
So lambda m becomes inversely proportional to concentration. Got it?
Yes,
Got
ma'am.
it? What is lambda m's definition? I told you from here you can collect. Is that? Yeah, see. I told you to mark these 2 lines. Don't change even a single word. This is the definition for conductivity. The conductivity of a solution at given concentration, at any given concentration, is the conductance of 1 unit volume. So if the concentration is high, since I'm fixing the volume, if the concentration is high, more ions. If the concentration is low, less number of ions. Because the volume of the solution is fixed. So conductivity of a solution at any given concentration is conductance of 1 unit volume of solution kept between the platinum electrodes at unit, kept between platinum electrodes with unit area cross section and at a distance of unit length. But what is molar conductivity? Molar conductivity of a solution at a given concentration, any concentration it can be, but you take that volume of solution which offers 1 mole of electrolyte. Is that clear?
Yes, ma'am.
Placed between 2 electrodes still at the same distance, but area of cross section keeps varying in order to accommodate that volume of solution. Is it okay? Aprameya, is it clear?
Yes.
Okay. I'm going to actually, sharp 7 o'clock, I'm going to stop the class. Okay. I have some work. Okay. What is the expression? Molar conductivity, therefore, is conductivity offered by V volume of solution, which offers me 1 mole of electrolyte when placed between electrodes at unit distance and area of cross section A. So this becomes the expression for the molar conductivity. Any problem with this? What is molar conductivity? How do you define? It is the conductivity of the solution which offers conductivity of V volume of solution, which offers me 1 mole of electrolyte placed between electrodes at unit distance and area of cross section A. Is that expression clear?
Yes, ma'am.
Yes, ma'am.
Okay. Again, surprisingly, or now you know that it is lambda m is inversely proportional to C and kappa is directly proportional to C. Here, the volume was fixed. With changing concentration, you are getting more ions or less ions. When you were doing conductivity
More
determination, no, when you are doing conductivity determination, the volume was fixed. The unit volume of solution. If the concentration is more, unit volume of solution offers more electrolytes. If
Yes.
the concentration is less, unit volume of solution offers less number of electrolytes. Clear?
Yes, ma'am.
But when you are doing molar conductivity experiment, you are not fixing the volume. You are fixing the amount of electrolyte.
Concentration.
So you are not even fixing the concentration. You are fixing the amount of electrolyte. Amount is different from concentration.
Okay, ma'am.
So amount of electrolyte is 1 mole, 1 mole. So if you have a concentrated solution, like 4m, the volume of solution that you must take will become 0.4. How much? 4 na? So 0.25 liters. Okay, lambda m is the conductivity offered by 1 mole of electrolyte present in V volume of solution. If the solution is concentrated, you take less volume. If the solution is dilute, you take
No.
more volume. More volume will offer me 1 mole. Is that
Yes,
clear?
ma'am.
Okay. So after all, it is the performance of only 1 mole of electrolyte. And when is it going to be best? When it is diluted. Because when it is diluted, when the concentration is low, the ions are separated out. Ions are well separated. The ions are free from interionic attraction. Clear?
Yes,
Yes.
ma'am.
Okay. Now coming to the expression for V. What is that V? V is the volume of solution which offers me 1 mole of electrolyte, correct? So supposing the concentration is 5m. What does it mean? Can we say 5 mole is coming from 1 liter?
Yes, ma'am.
Okay. So 1 mole will come from how many liters?
0.2.
1 by 5 liters, right?
Yes, ma'am.
Any problem, Ishan?
No, ma'am.
This is volume calculation. Okay.
Yes,
Volume
ma'am.
calculation. Okay. So if the concentration is 5m, 5 moles comes from 1 liter. We are not fixing the unit volume. Volume is not fixed. It's the amount of electrolyte. So the question is, what volume will be offering 1 mole of electrolyte? So 5 moles come from 1 liter. 1 mole will come from 1 by 5 liters. Any doubt?
No, ma'am.
Supposing this is Cm, C concentration. Then can we say C moles is coming from 1 liter? So 1 will come from 1 by C liters.
Yes, ma'am.
Yes, ma'am.
So this is the volume expression. So what can we do? Can we put it as kappa is equal to, lambda is equal to kappa times 1 by V?
Yes, ma'am.
Yeah, 1 by V. Okay, very good. Now, how do we represent kappa? Don't we represent it in Siemens per centimeter?
Yes, ma'am.
So the volume should also carry the expressions in centimeter cube only.
Yes, ma'am.
So can we say C moles comes from 1000 centimeter cube? Instead of 1 liter, I can say 1000 centimeter cube, na?
Yes, ma'am.
So 1 mole will come from? 1 mole will come from?
1 by 1000
1000 centimeter cube by concentration.
So can we now write here 1000 centimeter cube by volume, by C, by C.
Yes, ma'am.
Yes,
Which
ma'am.
is kappa expressed in Siemens per centimeter. This is 1000 centimeter cube per liter and concentration in C moles per liter. Is that fine?
Yes, ma'am.
So per liter, why am I bringing per liter? I could have written like this also, nothing wrong. But I'm just saying that in 1 liter, I will have 1000 centimeter cube. In 1 liter, I have got C moles. Both are same, no?
Yes, ma'am.
Okay. So can we say this liter gets cancelled? The centimeter inverse and 1 centimeter term will go off. So can we put it as kappa into 1000 by C expressed in Siemens centimeter square per mole?
Yes, ma'am.
Is that fine?
Yes,
Is
ma'am.
that fine? Okay. Now, I'm going to continue for 2 more minutes. Supposing, no, I want to do everything in SI units. That means kappa will come in Siemens per meter. The volume also
Yes, ma'am.
should be in meter cube, correct? Again, going
Yes.
back, if the concentration is C mole per liter, that means C moles is present in 1 liter, or it is present in 10 to the power minus 3 meter cube,
Yes, ma'am.
1000 1 meter cube is equal to 1000 liters. Apo 1 liter will become 1 by 1000 meter cube, or 1 liter is 10 to the power minus 3 meter cube. Do you get it?
Yes,
Yes,
ma'am.
ma'am.
So C moles is present in 10 to the power minus 3 meter cube. So 1 mole will come from how much?
1 by
10 to the yeah, 10 to the power minus 3 by C.
Meter cube per liter by C moles per liter.
Yes, ma'am.
I'll take this as the volume and substitute there. So what will I get? Kappa expressed in Siemens per meter, okay, into 10 to the power minus 3 meter cube per liter by C moles per liter. Again, per liter gets cancelled. So you will have kappa by 1000. Can I put that 10 to the power minus 3 in the denominator?
Yes, ma'am.
And the unit will be now what? It will be in Siemens meter square per mole.
Yes,
yes,
ma'am.
ma'am.
So these are the two expressions. And in most of the cases, we will be using this expression. That is because our conductivity cells have very small distance between the electrodes. So it's often measured in centimeters. So we will use this expression more than the other, but you should know both of them. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. So with that, I am going to stop the class. You want to take a, you have understood it well? Any problem in this?
No,
No, ma'am.
Okay, then I'm going to stop the class. Okay. So see you on Wednesday. See, again, I don't want to miss the classes. I will take as much as possible. If someday I'm not available, please excuse me. Fine. For this one. That's why I did not plan for a fixed holidays. Okay. Because I know that, no, many of the days you will also be available. I'll also be available. And some days I'll have to take leave. So that is why basically. Fine. Okay, children?
Yes, ma'am.
Okay, yes, no, fine.